So in this next video, we're going to look at something called the primitive root theorem. But what we're really looking at is this group UN and when is it going to be cyclic? So it was a couple weeks ago when we talked about the group UN. So let me remind you of it. We first of all remember that this is going to be our quintessential group for doing cryptography. So it's going to come back at multiple times. And remember, this was the group of multiplicative inverses in Zn. So this was the group of elements that had inverses, multiplicative inverses in Zn. And so let's look at this. So if I looked at Z6 or U6, this was the group of elements in Z6 that had multiplicative inverses. And we did some work and we saw that the things in U6 were going to be exactly the numbers from 1 to 5 that had no common factors with 6. So the factors of 6 are 2 and 3. So the things in U6 are the things that don't have any 2s or 3s that divide them. That's 1. We can't include 2. We can't include 3. We can't include 4, but we can include 5. So U6 is only 1 and 5. Okay. Notice that 1 and 5 are actually the generators for Z6, but that's something you can just keep in the back of your mind. We don't have to worry about that. So if we wanted to list the elements in U16, 16 is 2 to the 4th. These are going to be everything that doesn't have a 2 in it, has no factors of 2. So this is really just going to be the odd numbers from 1 to 15. So 1, 3, 5, 7, 9, 11, 13, 15. Notice, remember, these are exactly the same things that we said generated Z16, but they're also the elements in U16. U16 is a multiplicative group. The operation is multiplication mod 16. So if we're working in U16, we're working with multiplication. Okay. The things in U28, 28 again is 2 squared times 7. So we're looking for all the numbers that are relatively prime to 28, which means have no common factors with 28. So it means numbers that don't have any 2s as factors and don't have any 7s as factors. So it's going to be the exact same list that we saw up here. These are going to be exactly the same numbers from this list because the generators for Z28 were those exact same kind of numbers. So we're going to have that same list. That was 1, 3, 5, 9, 11, 13, 15, 17, 19, 23, 25, 27. Again, the group operation here is multiplication mod 28. And then finally, if we want to look at U31, 31 itself is prime. So we're looking at numbers that have no common factors with 31. Well, if you're less than 31, you're not going to be divisible by 31 at all. So everything from 1 to 30 will be on this list. So U30, 1, 2, 3, 4, 5, 6, all the way up to 30. Okay. This is a group with multiplication mod 31. Okay. If we're working with a prime number, then all the numbers from 1 to 1 less than that prime will be in U of that number. Okay. So that was just review of what UN is. So let's start out at kind of trying to get at the idea of when do we have cyclic groups here? So are these groups cyclic or not? So let's look at U8 here. So U8, 8 is 2 cubed. So U8 will be numbers that have no common factors with a 2 or have no 2's in them. So 1, 3, 5, 7. Remember the operation here is multiplication mod 8. Okay. And so now this is asking us to list the numbers in the groups or the sets generated by 1, 3, 5, and 7. Okay. So if the operation here is multiplication now, so we're multiplying, not adding anymore. So if I look at the things in the set generated by 1, that's going to be 1 itself. Then it's going to be 1 times 1. Again, it's multiplication because that's our group operation. 1 times 1 is just 1. 1 times 1 times 1 is still 1. So I'm stuck at 1 all the time, which makes sense because 1 is the identity here. If I look at 3, I'm going to have 3. Then I have 3 times 3, which is 9. 9 mod 8 is 1. So I'm back to the identity again. Once I get back to the identity, I've got everything I need. 5 is going to give me 5. 5 times 5 is 25. But 25 mod 8 is 1. So that's everything here. And then 7 will give me 7. 7 times 7 is 49. 49 mod 8 is again 1. Okay, so this means that U8 is not cyclic because none of these sets include all of the elements from U8. So U8 is not cyclic. Okay. It's going to turn out that some of these U groups are cyclic and some are not. So kind of a fun little fact here. So let's see if we can find a U group that is cyclic. So if we look at U9, 9 is 3 squared. So the things in U9 will be the numbers that are not divisible by 3's at all. So I have 1, 2 is okay, 3 is not okay, 4 is okay, 5 is okay. 6 is divisible by 3, so no 6's. 7 and 8 are both okay. Okay. And then this is asking me to list the elements in the set generated by 2. So I'm going to have 2. I'm going to have 2 times 2, which is 4. Okay. So in this case, I'm multiplying by 2. Okay. I'm going to multiply by 2 again to get 8. Okay. Remember, we're working mod 9 now. Okay. I'm going to multiply by 2 again to get 16. 16 mod 9 is going to give me 7. And multiply by 2 again to get 14. 14 mod 9 is 5. And multiply 5 times 2, I get 10. 10 mod 9 is 1. Okay, I got back to the identity, so I can stop there. If I forget to stop, then I multiply 1 by 2, and I get back to 2. As soon as I get back to 2, I found everything on my list. Okay, so let's see. I noticed that this thing, that 2 generates all of the elements from this list. I've got 1 accounted for, I have 2 accounted for, I have 4 accounted for, I have 5, I have 7, and I have 8. It's okay that they're not in the same order, that doesn't matter. What this tells us is that 2 generates U9, and so yes, U9 is cyclic. Okay? All it takes is finding one generator to show that we have a cyclic group. Okay, so what we saw is U8 is not cyclic, but U9 is cyclic, okay? So we might ask ourselves, when is UN going to be cyclic? And that's going to be the question that we'll answer in just a second. Before we do that, let me ask, is 8 a generator for U9? So that's asking, is U9 equal to the set generated by 8? Well, let's just look at the set generated by 8. So that's going to be 8. 8 times 8 is 64. 64 is one more than a multiple of 9, so 64 mod 9 will be 1. Once I've got to the identity, I've found everything. So 8, the set generated by 8 just contains 8 and 1. This is not equal to U9, so 8 is not a generator. Okay. So the big question that we have is, when will UN be cyclic? So that's my question. When will UN be cyclic? And that's what the primitive root theorem tells me. So the primitive root theorem, we're not going to be able to prove. It involves some interesting number theory that we don't really have the skills to do right now, but it's okay. We're just going to take this as a fact. So the primitive root theorem tells me that UN is cyclic if and only if n, the number inside, is of one of these forms. So if it's 1, if it's 2, if it's 4, or if it's a prime number to a power, or if it's 2 times a prime number to a power. Okay. P has to be an odd prime, so P is not 2, is really what this is saying. Okay. So let's look at a few examples and see how we apply the primitive root theorem. So let's look at this. So really what I have to do is I have to factor these numbers and see what kind of form they have. So if I look at U18, 18 is 2 times 9, which is 2 times 3 squared. I want the prime factorization. Okay, I notice that this is 2 times a prime number to a power. So that's of this form. So that's good. This is a cyclic group. So this is cyclic. We don't know what the generators are, and that's okay. We don't really need to know right now. Knowing when UN is cyclic is going to be very important for us for the Diffie-Hellman key exchange, which is going to be a cryptography application that we're going to use. So the primitive root theorem will come in handy over and over again this semester. So let's see. For U81, 81 is 9 squared. 9 is 3 squared, so we have 3 squared squared, which is 3 to the 4th. 3 to the fourth. 3 is a prime number, 4 is a power. So this is a prime number to a power. So this is cyclic. That's this form here. Let's see, 99 for U99. 99 is 9 times 11. That's 3 squared times 11. Well, that's prime to a power times another prime. That's not one of these forms, so not cyclic. U of 101, you may or may not know this, but 101 is prime. So this is of the form a prime to the first power. Well, that's okay. That's a p to the k. So a prime to the first power is always okay. So u of a prime number is always going to be cyclic. So this is cyclic. And then my last one, u of 222. We have to factor 222. I'll let you do the work, but this gets 2 times 3 times 37. This is the product of 3 prime numbers. That's not one of these examples. So this is not 2 times p to the k because I have 2 other prime numbers multiplied by it. So that's not works. So this group's not cyclic. Okay. So what you need to know from the primitive root theorem is you just need to know, like, we have to look at the factorization of our numbers, and then based on how they factor will tell us whether that U group is cyclic or not. This only works for UN. This is not going to work for like Zn. Zn is always cyclic. Un is only sometimes cyclic. So when we do the Diffie-Hellman key exchange, we're going to rely on using a group Un that is cyclic. And so we're going to have to be looking at UN where n is in one of these forms. Okay. So hopefully this made some sense to you.